In exercise 21, we are asked to minimize a cost function defined as this one, where x measures the manufactured tons of product A and y the same for product B. We have to calculate the minimum in the set where x is greater or equal than 1 and y is also greater or equal than 1. For it, as always, we start by calculating the first order partial derivatives, which are 4x cubed minus 4x and 4y cubed minus 8y. We make them equal 0 and solve the system. The first equation, I can take a common factor for x squared minus 1 equal 0, which has the solution x equals 0 and x equal 1 and x equal -1. Now I do the same with the other equation. I take the common factor for y, factor of y squared minus 2, which has the solution y equals 0, y equal root of 2 and y equal negative root of 2. So this function has a lot of critical points. The first one would be this one with this one, P2, this one with this one, P3, 0, negative root of 2. Now 1 with this one, and so on, P5, 1 root of 2, P6, 1 negative root of 2, P7, minus 1, 0, P8, minus 1 root of 2, and P9, minus 1 minus root of 2. All of these are critical points of C function, but the only one that verifies x greater or equal than 1 and y greater or equal than 1 is point 5. So this is the only critical point in the set A where we are minimizing the function. So the critical point of C in A is 0.1 root of 2. To know if it is a local optimum or a saddle point, we must calculate the Hessian matrix. Sorry, this matrix, this function is C H of C evaluated at any point is 12x squared minus 4, 0, 0, and 12y squared minus 8. Now we replace the critical point in the Hessian matrix, and we get 20, 0, 0, and 16. Sorry, this is 8. To study its sign, it is a diagonal matrix. We use the eigenvalues, which are 8 positive and 16 positive. Then the Hessian matrix evaluated at point P is positive definite, which means that P is a local minimum. This means, for example, that in P1, for example, if this would be P, this point, we have that P is a local optimum in R2, but we are interested in knowing what happens in, for example, this set. Maybe this point could be the global minimum in set A. So that's what we are going to study now. To study global optimality, we must study the convexity of the function in the set. The first thing is to know if the set is X-convex. This is a convex set because of two reasons. The first one, if we do the graphic, we can see that if we join any pair of points in A, the segment connecting them is fully contained in A, so A is convex. Moreover, A is the intersection of two upper semispaces, so AX is convex. Now we come back to the Hessian matrix evaluated at any point, which is this one, and we must study its sign. As it is a diagonal matrix, I have that its eigenvalues are 12x squared minus 4 and 12y squared minus 8. These signs can change, but we must be restricted to set A. So, if x is greater or equal than 1, then x squared is also greater or equal than 1, and 12x squared is greater or equal than 12, and then 12x squared minus 4 is greater or equal than 8, which is greater than 0. So the first value is positive, strictly positive. A similar reasoning we have with the second eigenvalue. Y is greater or equal than 1, y squared, it is also greater or equal than 1, 12y squared greater or equal than 12, 12y squared minus 8 is greater or equal than 4, which is greater than 0. So the second eigenvalues is also positive. Then the matrix evaluated at any point is positive, definite, not in R2, but it is in A. and C is convex in A. Then we have a critical point in set A, and that C is convex in A, then P is a global minimum of C in A. Moreover, as the Hessian matrix at any point was positive definite instead of semi-definite, we can conclude that P is the only global minimum of F of C in A. So the answer would be that we must manufacture 1 unit of product A and root of 2 units of product B to reach the minimum cost, which would be C evaluated at point 1 root of 2, which is 1,495 units.